Okay, I think it's time to start. Hello, I'm Benjamin Wright. I'll be your instructor for this class, which is an intermission. It's an intermission, so it's not a normal class for this Saturday series, but it's fine. We're gonna have some fun with game theory. So in case you don't know me already, I'm a high school senior who's going to go into college at MIT this fall. I like math, I do it a lot. I might even do it as my major. So it's my pleasure to help teach you all today. So today for co-hosts, we have Dylan K. Liu. He'll be our main TA, but Naveen is also here in case you have questions and Dylan can't answer them. Okay. So let's get started. Okay. Okay, so what is game theory? Game theory is you want to try and analyze how games work, but to do so, we kind of need to make some assumptions about what games are and how players act. It's really hard to model people, like real people, because they're irrational or they have really weird desires. And you can still do that with game theory, but that's complicated. So what we're going to do is we're going to assume that we're dealing with rational people. And for now, at the very beginning of this class, we're going to assume that rational people are greedy. And that means they always take the best option that's available to them. If one option strictly gives them more points than the other option, then they're going to take that option. They're greedy and logical. And we're going to assume that they have like infinite processing power. So they're like supercomputers. Okay, that's the base assumption. So what are we going to do with rational people? Well, this introduction to game theory will focus on finding equilibriums. And equilibriums are spots that the game naturally falls into. So when I say spots that the game naturally falls into, like if we go out of game theory and we draw like a graph, let's say this is like a hill, and you have like a ball that's rolling. Both of these spots can be considered equilibria because if a ball falls in here, the ball isn't going to keep falling anymore. This is like a state. These are stable equilibria. In game theory, there's a similar concept as well. And equilibria in game theory is all players have a strategy and no player has an incentive or a need to change strategy. So this doesn't mean that an equilibrium is the best for each possible player. All it means is that if you have if you're in an equilibrium, if a player changes their strategy to any other strategy, then immediately after, that player will either have the same result or a worse result. So because rational people are greedy, they don't feel a need to change out of an equilibrium because otherwise they won't get a better score. So a popular game theory problem that we will revisit is the prisoner's dilemma. The prisoner's dilemma is you have two criminals in prison, and they're being interrogated, and they can either cooperate with each other, which is give the same story as each other, or just cooperate is you don't reveal information that would incriminate your partner. That's cooperating. Or you can defect, which is you spill the beans. You tell the interrogating officer all the bad stuff about your partner, and then because of that, because you were helping the police, they give you a lower sentence. So the prisoner's dilemma is if you both cooperate, then both of you have like a small number of years in prison. Let's say 2 years in prison. If one cooperates, one defects, the cooperating gets, the numbers don't really matter, but we can say like 7 years. The defector gets 1 year. And then if they both defect, then we can just say that they all get 5 years. Okay, this is an example of the prisoner's dilemma. And the reason it's the prisoner's dilemma is obviously both of them cooperating will be the best for the two of them. So in a real life situation, if they're able to communicate with each other, they'd want to both cooperate. However, if we assume rational people with the greedy assumption, we know that if they have a choice that's better, they're going to take it. So in this case, at least, both cooperate is not an equilibrium. And that's because each player has an incentive to switch. Because if you defect, your years in jail goes down from 2 to 1. So both cooperating won't help. In fact, both defecting is the equilibrium. Once you both defect, any change will immediately make it worse for the player. And it just seems so irritating to me, or probably to you guys as well, because obviously cooperating is better for both of them, and yet the equilibrium is the exact opposite, which is both defecting. So you should keep in mind that equilibriums are not always like what the best outcome is, but just what it is. No one has incentive to change. Okay, now that these definitions are out of the way, we can go into some more mathy bits. So how do you represent a game in mathematical terms? Well, a very common way of doing it is drawing grids like this. So the rows correspond to player 1's choice, and the columns correspond to player 2's choice. So to make it simple, let's just have each player have one choice. Player 1 can choose A or B, and player 2 can also choose A or B. Now in these squares, we put how much each player can earn. So you would write it as like 1, 5. And this pair means if both players choose A, player 1 gets a 1 and player 2 gets a 5. So this is an example of a game. There's a simpler type of game, which is called zero-sum games. And here we only need to place one number like this. This is a zero-sum game. And it's called that. It's called a zero-sum game because the sum of the points each player gets is 0. Essentially, if both players choose A, player 1 gets 1 point, which is and that's equivalent to also giving player 2 -1 points. It's a zero-sum game, which means if one person benefits, the other person gets hurt. So this game is actually equivalent to directly putting 1 -1, 2 -2, -3 3, 0 0. So anytime you have a zero-sum game, you can always just turn it into a non-zero-sum game. So now we can get into strategies of how to find equilibria. So there's a concept of a flow chart. And a flow chart is a map, or like you place arrows onto one of these grids that tells you where each player prefers to go. So let's apply it to a zero-sum game first because it's easier to see what's going on in a zero-sum game. So if both players are currently choosing A, that means right here. That means player 1 is getting 1 point and player 2 is sad. I'm going to draw an arrow from the right to left here. And what this means is that if player 2 would rather choose A than B if player 1 is choosing A. What you can imagine is if you ever landed on in this situation where player 1 chooses A, player 2 chooses B, player 2 would want to follow this red arrow and go to the AA square because it's better for them. Player 1 gets less points and player 2 gets more points. And we can keep drawing arrows for this grid. So player 1 likes to have larger numbers. So this arrow would go up. And similarly, this arrow would go up. Player 2 likes lower numbers. So player 2 would go here. So as you can see, we now have arrows through all these squares. So to find the equilibria, we just follow these arrows and see where we end up. If we start here, we know that both of these regions, both directions of change are actually better for one of the players. So if we move to the left, then player 1 would move up. If we move up, then player 2 would move to the left. So actually, no matter where we start, if we follow the flow chart, we end up with this upper left corner as the answer. So the equilibria is actually both players choose A. This is fancy notation, but this literally just means player 1 chooses A, player 2 chooses A. This is equilibria. So flowcharts. Flowcharts are nice when they work, but there's a problem when they don't always work. And there are two situations in which this becomes a little bit different. So if the flowchart is instead something like this, then we actually have two equilibria if we follow the previous method. Both this square and this square are kind of stable spots you fall into and then you can't move out of. So in this case, you would have two equilibria. But there's even a situation where you don't have any equilibria following this flowchart method. And that case is when you have arrows going in a cycle like this. Here, no matter how you follow the arrows, you're going to keep moving over and over. You never fall into a stable spot. So this is a situation where we have no pure equilibria. And I use the word pure because there actually could be equilibria, and there most likely are. They're just not the type of equilibria we've been talking about. So far, we've been talking about pure strategies where one player always chooses one strategy and the other player always chooses one strategy. If you look at this equilibria down here that we found, A, and A, this is an equilibria where player one always chooses A and player two always chooses A. But there are strategies that are mixed. For example, you could have a strategy which goes something like 40% of the time choose A, and 60% of the time choose B. This is a mixed strategy. So when you have a flowchart in a cycle like this, you're actually going to end up, you're most likely just going to have to solve and find mixed strategy equilibria. So how are we going to find mixed strategy equilibria? Well, first let's try and create a game that follows this flowchart. Okay, this is a game that follows the flowchart. What do you all think? How do you all think we should solve for the mixed strategy equilibria? Actually, why don't I make this simpler? If I instead change the numbers to be like 2, 1, 2, 1, it's the same game, but maybe this will help you think of it easier. Yeah, I can make this into a word problem. I believe a soccer shot can mimic this situation. So if we have a goal, and we have a soccer ball, and we have like a goalie, and we have a shooter, and the shooter can either shoot left or right, and the goalie can either save left or right. This is a zero-sum game. Like either one team wins or the other team wins. There's no way for both of them to win. So this goalkeeper game can be something like this. Let's say player one is a shooter. You can either shoot left or right, so there are two options. And the goalkeeper can either block left or right. So if the goalkeeper blocks left and the shooter shoots left, then the shooter gets 0 points. But if the shooter shoots in a different direction than the goalkeeper blocks in, he gets a score, so 1 point. And once again, if they choose the same thing, he gets 0. So this game is like taking one soccer shot. So these two games are actually pretty much the same thing. And they both have the same equilibria. Now, if I ask you all to find out what the equilibria for this game are, you guys should be able to intuit it, right? Post in chat if you know the equilibria for this. Shooting straight is not an option. There's only left or right. So this is a situation that I was talking about earlier, where the flowchart is a cycle. There's actually no equilibria. There's no pure strategy equilibria, because the flowchart is the flowchart looks something like this. So none of the arrows point towards one spot. So we don't actually have any equilibria. And that makes sense, right? If you have like left, both of them are choosing left, then the goalkeeper wants to choose right. So he's not satisfied with this strategy. And if you have like left, right, then the shooter wants to oops, I made a mistake. If you have a left situation, it's the shooter that wants to go right, so he'll get a point. If you have right, left, then the goalkeeper wants to go right, and etc. etc. Anyway, so whatever pair of pure strategies you put together, one of the players will always be dissatisfied and want to change, and that's what this cyclic flowchart means. It means there's no way we can get like a pure strategy equilibria. But there obviously is an equilibria, which should be pretty clear. But the strategy is just you have 50% left, 50% right for both of them. So you essentially just randomly choose left or right and you shoot. So this turned out to be the equilibria for this game. And the reason why this is the equilibria is because if you know the other person is randomly choosing between left or right, you have no desire to change, to go all left or all right. If the other person is randomly choosing, it doesn't matter what you do, it'll still be a 50-50 shot, which is why this is an equilibria. If you all remember, the definition of an equilibria is if you know the strategy of the opposing player, then any change in strategy on your part alone will not immediately give you more points. And if one player is going 50-50 and you're also going 50-50, if you change your strategy, you don't get any more points. So this is a situation that we can just intuit through, but we want a way to solve for the equilibria in general. And the way we're going to do that is we can actually apply the definition of rational. So the definition of rational tells us that if a player has a better choice, they will choose the better choice. Now, this is actually more powerful than you expect it to be, because if we have a mixed equilibria, a mixed strategy equilibria, that means if I write in the bottom here, that means, for example, player 2 can choose 30% A and 70% of the time choose B. This is just for an arbitrary game. If this is actually the player 2 strategy in an equilibria, what this means is that choosing A and B have to give you the same value or the same expected output. Because player 2 is a rational, greedy person. If A gave more points than B, then he would just choose A. So if for mixed equilibria to make sense, A and B have to be the same value to player 2. Like if going left and right both gave you like 5 points, then you wouldn't know how to decide between the two. So you can kind of do like 50% one or 30% one of them, etc. So if we actually want to look for mixed equilibria solutions, we can do this cheaty thing where we set the expected output for two options to be the same thing. So how do we do that? First, we're going to assign variables. Let's say player 1 has a p probability of choosing left and a 1 minus p probability of choosing right. Then what is the expected output when the goalkeeper chooses left? If the goalkeeper chooses left, well, there's a p chance that the shooter will also choose left, in which case the total value is p times 0. But there's also a 1 minus p chance that the shooter will choose right, in which case player 1 gets 1 point. So all in all, player 1 will get 1 minus p points on average. So if the goalkeeper chooses right, then what happens? There's a p chance that player 1 chooses left, in which case player 1 gains 1 point. And there's a 1 minus p chance that player 1 chooses right, in which case they get 0. So there's p points on average given to p1. So by what we just said earlier, for there to be a mixed strategy equilibria, we need these two outcomes to be the same, essentially the same, in the goalkeeper's eyes. So we can set p equal to 1 minus p. And this just gives us p equals 0.5, which is exactly the strategy we talked about over here. So this tells us that the equilibrium strategy for the shooter is just to go 50-50 left and right. Okay, it seems some of you are confused. If you're confused, please ask our TAs like Dylan Liu, even Naveen. They're here to help, and game theory is a kind of confusing subject. Okay, this was an example. This was a zero-sum game example. We can apply this to non-zero-sum games, and hopefully that will make it a bit easier to understand what's going on. Okay. So I'm creating a game. I guess guess I can show my thought process when I'm creating this game. So the game is kind of boring if the flowchart is not in a cycle like this. So I want the flowchart to look like this cycle, so that we can actually have mixed equilibria solutions. So that means that this bottom right corner needs to be better for player one than this top right corner, which means this would be like a 4, or any number greater than 3, really. And then to the right, we need the second number to be less we need this number to be less than 3. So we can put this as like 2. And this gives us a game that is kind of interesting. Okay. So how are we going to solve this? We're going to set probabilities again. So we're going to have a p chance that player one chooses A. So then there's a 1 minus p chance that it chooses B. And we're going to, I would do Q, but Q looks too similar to P. So I'm going to say X. There's an X chance that player 2 chooses A. So there's a 1 minus X chance that player 2 chooses B. So again, we can do the equating expected values thing. I'm going to write some notation. What this scary E means is, on average, what does player 2 get from choosing A? What does player 2 get from choosing A? There's a p chance that player 2 gets 0. This 0 corresponds to that 0. And there's a 1 minus p chance that player 2 gets 3, which is this 3 right here. Remember, player 2 gets the second number in these ordered pairs. Player 1 gets the first number in these ordered pairs. Okay. So what does player 2 on average get from choosing A? From choosing B, the other option? Well, now we do the same thing, except you look at the right column instead of the left column. So to find out what P is, we can set these two equal to each other. And we get that 3 minus 3P is equal to 3P plus 2 minus 2P. Which is equal to 2 plus P. So if we solve for this, we get that 1 is equal to 4P. So P is 1/4. So we can replace P with 1/4 here and 3/4 here. Now to get what X is, we have to go the opposite direction. So far we've been getting P. To get X, we have to set the expected value of P1 choosing A equal to the expected value of P1 choosing B. Now it's the same process as below. If P1 chooses A, there's X times 5 plus 1 minus X times 3. And on the right, it's X times 3 plus 1 minus x times 4. So if we solve, we get 3 plus 2x is equal to 4 minus x. So 3x is equal to 1. So x is 1/3. So here we go. So this is our equilibria. Our equilibria is player 1 has a 1/4 chance of choosing A, a 3/4 chance of choosing B, and player 2 has a 1/3 chance of choosing A and a 2/3 chance of choosing B. And we can apply this tactic to many other different types of games. Okay, I'm going to assume you all understand this. You should ask TAs. Please ask TAs if you have questions. I know this is confusing. If you encounter larger games, for example, if we have like a 3x3 game, hopefully you will be able to reduce it to a 2x2 game. Usually the method is through something that's called domination in game theory terms. We can remove columns or rows if a column or row gets dominated by another one. And this is just applying the assumption that the players are rational here. If choice C for player 2 is worse than choice A or B strictly, then we can actually just eliminate choice C. And an example for how that happens would be if we have like comma 5, comma 9, comma 7, and then choice C is comma 3, comma 8, comma 5. So here, player 2C is dominated by player 2 choosing B, because every single row, every single row, column C is beaten by column B. 5 is better than 3, 9 is better than 8, 7 is better than 5. So we can just eliminate this column, and now we've gone into a 2x3 game. So hopefully, once we've gotten this to a 2x3 game, we can do another domination. Once we've gone into a 2x3, domination no longer has to include games column C. So we only have to check two positions for a row getting dominated by another row. Let's give an example. If I put these values, now player 1 choosing B is dominated by player 1 choosing C, because 3 is less than 5, 2 is less than 10. So I would cross out these two. And remember, it does not matter what these two numbers in column C are now, because column C has already been dominated. We don't have to care about that anymore. So in this manner, we've reduced this game to a 2x2 game with options A and C on the left and A and B on the right. So if you encounter a really large game like this, hope that you're going to be able to reduce it. If not, it's hard. There's hope if you can't reduce it fully. And that hope comes in when you reduce it to a 2x n game. If you have like 2 rows, but a large number of columns, etc. So we can actually solve this, find the equilibria for this game still. And we're going to do it. We're going to set X to be the probability that A is chosen for pair 1. Then we're going to create a graph. I'm going to make this a zero-sum game for now. Zero-sum games are nicer. So since X is a probability of choosing A, X can go from 0 to 1, and we're plotting X at the bottom. Then at the top, we're going to put points. Points earned by player 1. So there are multiple strategies that player 2 can give. Player 2 can get A, B, C, D, E, or F. These are all strategies that player 2 can do. So how are we going to determine which one is the equilibria? Well, we can actually graph each individual one. Let's say column C has numbers 3 and 1. That means choosing C gives you 3x plus 1 times 1 minus x. This is, again, the expected value. So this is 1 plus 2x. So we can actually graph this. This is y equals 1 plus 2x. And this is strategy C. And we can keep going and graph the other strategies. Let's say F is like 2 and 4. That means F gives 2x plus 4, 1 minus x, which is 4 minus 2x. So F would be something like and that's F. And if you keep going, we're going to get lines like this, and perhaps useless lines like that. And let's pretend that we've graphed all the lines. Now, how do we determine what the equilibria is? Well, we keep in mind that player 1 wants to maximize the points earned by player 1, and player 2 wants to minimize these points because this is a zero-sum game. So X gets to choose a position down here. Like X can choose here or here or here or here or here, etc. So X can choose the X coordinate. But once that happens, player 2 can choose which of these colored lines to pick. So if X1 chose a spot over here with this marked with this red tick very close to 0, player 2 can choose any of these options because player 2 can choose the colored line. So player 2 would choose this bottommost point. So it turns out that the only parts of these lines that we actually care about is what I overlined with black here. No matter what player 1 chooses as the X value, player 2 will choose a point on this black line. So that means that player one would want to choose this x value here because it gives you the highest points on this black bottom line. So this tells us what x is and x value. And to find out what the strategy for player two is, we first look at which two lines are intersecting at this point. So I didn't give these lines names, but let's just say that the red line was line A, and oh yeah, and the blue line over here was line F. So at this point, both A and F have the same expected value for player two. And if you remember from mixed strategy equilibria, when you have the same expected value for two choices, then your answer, your equilibria, is going to be a mixed strategy of those two. So player one strategy is just like x chance of A. We've already found what x is at the bottom. And player two is going to be like p chance of A, 1 minus p chance of F. We just need to find out what p is. And the way to find out what p is we want to make sure that player one will not feel a need to change its x value. How are we going to do that? Okay, here's the part that's a bit tricky. We can draw a new graph now. But now we only need to draw A and F. The other lines, we have already canceled them out. They're not part of equilibria yet. We don't have to care about them. So by the definition of equilibria, if we go to any other point, any other x point, we need to have either the same value or a worse value. So if player two always chose A, that means we only focus on the red line, then x can just be moved a bit to the right, and player one would get a higher score. So x cannot be an equilibrium. Similarly, if player two always chose F, then x could just be moved to the left, and player one would get a higher score. So the only way for player one to not feel a need to move is if we get a horizontal line in here somewhere, so that every single position will give player one the same value. And we can get this orange line, not sure what color it is, it's more like a gold line. We can get this gold line by making a combination of A, the red line, and F, the blue line. So what that means is P times the A line. What is A? A will be something plus 1 minus P times F. We know what F is here. F is 4 minus 2x. So this will be the gold line. this is very tricky, so let me try and explain it. What we're doing here is based on the chance of choosing A and the chance of choosing F, the gold line, which is a combination of, which is what P1 actually gets, you can find out the gold line by just saying, hey, P times what I get from A plus 1 minus P times what I get from F. A will be some linear combination, like let's just make it 2 plus X. That may not actually be what it is, but just for the sake of getting some numbers. So now we have an equation for the gold line. We want the gold line to be a constant horizontal line. So that means the x's need to cancel out. It has to have a slope of 0. So having a slope of 0 means that px plus 1 minus p times negative 2x equals 0. I took the terms that have an x and set them equal to 0. So then in this manner, we can actually solve for what p is. P minus 2 times 1 minus p is equal to 0. So minus 2 plus 3p is equal to 0. So p is actually 2/3. So yay, we found out what p is. And you've already have what x is. This x looks kind of like 7/8. So let me just say 7/8. Well, actually, I probably shouldn't do that. We can find x as well. We already have x. So this gives us the equilibrium for a 2/n case. I think this is pretty cool. Essentially, you get a whole bunch of lines, and then one player wants to minimize, one player wants to maximize. So you find an equilibrium. Then you have two lines intersecting each other, and then you add them up in a special weighted average that turns into a horizontal line. Okay, we don't have a lot of time, and I hope to get through more. So I just have to speed through some summaries instead of going through in depth for the rest. Okay, so there are different types of ways to formulate games than just having a matrix, and the way you'll see games formulated is through a tree. Here, player 1 gets to choose A or B, and then once here, player 2 can choose a different choice, like C or D. C or D. If I just leave it like this is a pretty simple game, but you can keep going down. And in some places, you can go further down in some nodes than others. And you can have values like 5, 7, -3, 2, 4, 0. And this is also a game. And you can solve for probabilities. I would go in more depth, but I don't have time. So let me just give you the two tools you're going to use. So tool 1 is domination. When one choice is clearly better for one player always, you can just cancel out the choice that's obviously worse. And the second tool is when you can't cancel out something and you can't find a pure strategy, you're going to set expected values equal. Essentially, if you can't cancel something out, then your average outcome for choosing a choice should be the same as the average outcome of choosing the other choice. And with these two values, you should be able to calculate the probabilities of choosing the other choices for an equilibrium. There's another type of game tree, which is pretty annoying to deal with. But when you have information asymmetry, then things get complicated. In the matrix, both players always know what the other player is doing. But here, when we write like a game tree, players don't always have to be able to know, they aren't always able to know what the other player chose. So we denote this as a dotted line here. And the dotted line tells you that the player in one of the dotted line positions does not actually know which position there are. So this game tells us that player 2 doesn't actually know if they're in the left branch or the right branch. So only player 1 knows this. This is information asymmetry. You can still use these two tools to solve information asymmetry trees. You just have to realize that the probability of P2 choosing left in the left column, in the left branch, if I denote that as X, you have to mirror that on the right branch as well. Because player 2 doesn't know which branch they're on, it has to be the same variable. Okay. I'll leave it up to you all to investigate complicated trees and figure out how to solve them. It'll help you learn how to do probabilities and combinatorics better. I guess as a closing note, I want to say that so far we've been dealing with greedy players. And greedy players apply to a lot of situations in real life, but there are also many cases in real life where people want to cooperate, or people don't always care only about their own gain, but about everyone's gain. And there's a lot of game theory. There's a lot of game theory theories about how people should cooperate the best for each other. Let me give an example game. So let's say we have cities A, B, and C. And we have this center. Maybe the center has like valuable watcher or valuable supplies or something. So all the cities A, B, and C each need to be visited by a truck from the center. So if I mark how long these roads are, if the players don't cooperate with each other, what's going to happen is player A will have to, city A will pay for the truck to go directly to city A and then directly back. So A will pay for 1,000 units of distance. And player B will go from B and back. So B will pay for 900. And C will go directly to C, directly back. So C will pay for 500. But this clearly isn't the best way to have all the people like visited by trucks. What we want to happen is we want the truck to just make a cycle along like this. And therefore the truck can visit every single city, but not waste time going over the same paths over and over again. So in this case, the truck will only spend like what? 1,500 in the green track, which is clearly better than each player going their own. So in this case, cooperating is clearly better, so they all cooperate. But how do we determine how much each city pays for? Cooperating is better, but it's not actually clear how much each player contributed to everything. And there are different techniques for how you decide how much each city gets paid for. The easiest way, or I guess one of the most intuitive ways of doing it, of finding out is you calculate the Shapley value for each city, and that's how much each city needs to pay. And there's another technique called the nucleolus, which is another way to find out how much each city is paid. Since I don't have time to go over these, I'm going to challenge you all. You guys should think about this problem on your own. And how do you think each city should be paid? How much do you think each city should pay for the truck that's driving? And after you've thought this through, you guys should search up Shapley value nucleolus. It's pretty cool. So that's it for today. Thanks for coming to this intermission for game theory. I hope you've enjoyed. I hope you weren't too confused. And I hope you guys are interested in learning more advanced game theory now. Remember, there's always more math to explore. Never feel like this is it. Thanks for coming. You guys can leave now. I'll be staying afterwards for questions, so you can stay. But for the rest of you, see you all later. Bye.